So now I will introduce our speaker today, and I really feel honored to introduce a person like Professor Peter Braun-Munzinger, who is currently the scientific director at the Extreme Matter Institute at GSI. So to start with, he obtained his PhD from the University of Heidelberg and then started his professional career as a research associate in Max Planck Institute for Physics in Heidelberg. And then in his long career, he has served scientifically as in many positions at the State University of New York at Stony Brook, Brookhaven National Laboratory, GSI Darmstadt. He was a spokesperson of AGS E814 collaboration at AGS Brookhaven. And then he was a spokesperson of AGS E877 collaboration. Then he was also a professor of physics at Technical University Darmstadt and GSI at the same time. He was the project leader of ALICE TPC, and there are many more positions where he has served scientifically. He was an associate editor of Physical Review Letters, and then Nuclear Physics A, European Physics Journal A. At the current moment, he is the scientific director of Extreme Matter Institute, EMMI, Helmholtz Alliance on Cosmic Matter in the Laboratory, as I have mentioned earlier. He has also served as members of numerous important committees guiding the research in this area of physics, as a member of User Executive Committee, Brookhaven National Laboratory, member of Department of Energy Nuclear Physics Review Panel, member of Phoenix Executive Committee, and a chair of Board of Directors, ECT Trento, Italy, member of Scientific Policy Committee, CERN, member of Committee on US-based Electron-Ion Collider Science Assessment. I am just naming only few of a long list of memberships he has in the important committees. And he has also obtained awards, important awards, as few of them to mention: Werner Heisenberg Medal for von Humboldt Foundation in 2008, Lise Meitner Prize of the European Physical Society in 2014, Stern-Gerlach Medal of the German Physical Society in 2019, just to name a few of them. He has more than 500 scientific publications, and he has given invited colloquia and talks of over 300 occasions. He has, of course, produced a lot of physics students, PhD students, and postdocs, have worked with them, who are currently in all over the world as a senior scientists and professors in many universities, research institutes. He is a school. So with these few words, I invite Professor Peter Braun-Munzinger, and I would also like to mention that as a postdoc in GSI, an opportunity to talk to him personally on a regular basis. Cherish that memory. Peter Braun-Munzinger. Peter, it's now you all.
Oh, okay, thank you. So Priya, thank you very much for this very kind words introducing my talk. To be here and to share with you some ideas of what we have been working on. So let me see what
Can you all see?
Yeah, I can see.
Yes, I can see it. It's not full screen, but
is it full screen now?
Yeah.
Yes. Okay.
Oops, I have to stop it.
Okay, so I think thank you very much for this help. So I will talk about the QCD phase structure. This will be a talk of recent work, which will start with a short introduction and a brief survey of what we have learned of what I would call the description of hadrons in the large volume limit of QCD. That is realized for sure in lead-lead collisions at the LHC, but also in gold collisions at RHIC and at lower energies. I will make a short digression to small systems because that has been recently addressed in many areas. And I will go on to make a few important remarks, I hope, on fluctuations, net barrier number fluctuations. And then I will share with you some of our most recent ideas about open and hidden charm. This will be something which is not yet all published, it's all new. But it's something which we want to address in the next years at the LHC. And I would like to call that the multi-charm hierarchy and its relation to deconfinement. And I will conclude with a few words about the future of the field, in particular at the LHC and at RHIC. Okay, so let's go to the next slide. So this is something you all know, but I still would like to comment on it. The timeline of matter in the early universe. So we all know that there has been an exceptional period of something which is not yet very well understood, but nevertheless very important. It's called inflation. Inflationary expansion of the universe. Where that ended in time, we don't know. The standard models have it very early, let's say 10 to the minus 32 seconds, but it could be that inflation lasts much longer. I will not discuss that here. Now, between 10 to the minus 32 and 10 to the minus 12 seconds, cosmic matter consists mostly of massless particles and fields. Of course, the particles will acquire only mass through the Higgs boson after the electroweak phase transition, so that's 10 to the minus 12 seconds. And it is the yellow shaded region of the time when the quark-gluon plasma phase dominates, where particles will acquire mass through the Higgs mechanism, and the QGP consists of quarks, gluons, leptons, and the antiparticles, photons, C's and W's and H. They're all in equilibrium, but as the temperature in the expanding universe will keep on going down, it means that some particles, especially the heavy ones, will freeze out and be there only in very tiny numbers. But for most of the particles we now know, there will be a phase transition around 10 to the minus 5 seconds, where hadrons are produced. And at that phase transition, which lattice calculations on the for QCD, solving QCD on the lattice tells us that pseudo-critical temperature of that phase transition is about 155 MeV. All the hadrons are produced, and I will spend most of my time on that phase. It is still important to recognize that between 10 to the minus 5 seconds to 1 second in the early universe, even neutrinos are still in equilibrium. So the leptons and neutrinos are an integral part of the early universe phase, but they do not exist in the system in equilibrium produced in nuclear collision. So you cannot say that the matter we produce is all equal to what is produced in the early universe, but some key parts are equal. Okay, next slide. This is a figure which is something I will go quickly over. This sort of shows you what happens in a collision between two Lorentz contracted ions, where they have, after a phase of initial hard scatterings, there will be approach to and eventually equilibrium reached, the so-called Qcd phase, which then leads, after the hadronization and phase transition, to the particles which we will detect. And on the right-hand side, you see a plot picture made out of the Alice TPC, which you have now realized, or probably knew, that I spent nearly 20 years of my life to get that detector going. And I think it was very, very interesting to see the first pictures from heavy ions coming out, and this is one of them. So next slide. Can you move? Okay. So this is just a survey of what's going on in the lead-lead collisions at Lhc energy, at the highest energy available at the moment. So we have altogether, the last one was in November 2018. You all know that since 2019 and 2020, there was a long shutdown that is going on, unfortunately, because of various delays, including what came from COVID, until something like maybe even early 2022 schedule. So there will be another year of preparing for the next run, for run 3, and I will come back to what run 3 will bring and might bring to us. Let me just say that in a central collision at Lhc energy, at the highest energy, more than 32,000 particles are produced, more than 32,000 hadrons are produced. And of course, we cannot measure all of them, but we can measure a fraction of them and conclude on what actually comes out in the what kind of system comes out, and what is the nature of the system. And even for that snapshot, you need to measure something like 3,000 to 4,000 particles at the time, and measure their identity and momenta. Next slide. So this is a nice picture. I like that picture because it gives you an idea of the size of systems. The Alice detector inside, in red, Alice magnet, the huge L3 solenoid. You see for size, the person in the lower middle, that gives you an idea, gives you a feeling for that, and it also tells you, if you want to work on this detector, you need to have training to work at heights. You have to be something like a mountain climber, and quite a number of people actually have that experience and have that training and did that and enjoyed it. The middle of where you see a hole in the middle, that is where the inner tracking system would normally go. It has been removed for this photograph here. And the blue part around that is the TPC, 5 meters in diameter and 5 meters along the cylinder. And outside of that is a transition radiation detector time of flight and electromagnetic calorimeters. And on the other side of, and not visible from here, is the muon system. Next slide. Can you move to the next slide, please?
Priyo, can you mute your mic?
Okay, so this tells you how we do particle identification. And one of the important parts in that is that, and important lessons when we actually turned on lead collisions, is that you don't see just electrons, muons, pions, kaons, and protons, but you see lots of heavier particles shown here, deuterons, tritons, but we also have measured hypertritons and helium-3 and even alpha and the antiparticles, and they all come out. They are very loosely bound nuclei. Loosely bound means their binding energy is only a few MeV, and the energy to remove a nucleon from those particles is sometimes only a few hundred keV. Even though those energies are tiny, they are produced at reasonably large quantities, such that you can see it in a simple picture like that. Next slide. So here we start now the scientific part after the introduction. So if we want to understand how hadron production is related to the QCD phase boundary, what we have to do is measure the momentum and identity of all produced particles, etc., and analyze that all together. And what we would like to see from that is whether one can actually get detailed information on the existence and position of the phase boundary. Next slide. Means first we will concentrate on hadrons with up, down, and strange quarks and see how their production actually tells us information, what the state of matter is when these hadrons are produced. And in the next slides, you see the latest of this kind of analysis. We call that statistical hadronization of U, D, and S hadrons. A comprehensive review of the state of that is given in this Nature article, which is cited here on the top. And what you see in the plot is the yield of hadrons per unit rapidity. We measure over plus minus 1 unit, so 2 units of rapidity, nearly plus minus 1 unit. And you see in that plot the yields compared to predictions of what we call the statistical hadronization model, to which I will come in a little bit more detail in a second. And you see that these are the lines, the horizontal lines, the red points are the data points. And you see that actually this prescription works extremely well, not only for pions, kaons, and protons, but also for lambdas, cascades, omegas, and their antiparticles, and for many people, very surprisingly, also for deuterons and helium-3 and even hypertriton, where the lambda is only bound by 130 keV, while the temperature is 155 MeV. And for helium-4 and anti-helium-4, it also works perfectly. And so we have a detailed description of the particle production, and what comes out from that prescription is a temperature which is 156.6 plus minus 1.7 MeV. And that temperature is very, very close, actually surprisingly close to what our theory colleagues using Lattice QCD have computed as the temperature of the pseudo-critical temperature of the QCD phase transition. The baryochemical potential turns out to be 0 within uncertainties, and that, of course, is also visible when you see that particles and antiparticles have the same yield. Now, on the way to this, I would say, impressive result, there were a number of issues to be faced. The most recent one, that the first results had fewer protons in the measurements than we had predicted. But this issue, the so-called proton puzzle, was solved in an S-matrix treatment of the interactions, and I can comment later on that in more detail. Of course, there are not only data like that at Lhc energy, but there are also data at lower energies. And at each energy, one gets a pair of temperature nu B values, and those then to the establishment of the experimental establishment of the QCD phase diagram, and we can compare that to, for example, lattice predictions. Next slide. So important to note is the following. We have this temperature of 156.5 or 156.6 MeV. But there is an uncertainty because in order to compute that, we have to know the hadronic mass spectrum, not only from low masses where it is actually well measured, but for even masses larger than 2 GeV, where it's only poorly measured. But if you look at these composite particles, deuteron, helium-3, hypertriton, and alpha, and their antiparticles, there is no feeding from the heavier particles, and the hadronic mass spectrum is unimportant. But we get essentially, and within uncertainties, the same temperature on ME 159 plus minus 5 MeV, independent of the hadronic mass spectrum. So that's an important result. Next slide. The thermal pattern established for particle production at Lhc energy is particularly clear when you plot the yield divided by the spin degeneracy factor versus the mass of the particle. Now, remember, at Lhc energy, there is no chemical potential. So therefore, all the production, the thermal production depends only on the mass. In particular, that means that also strangeness doesn't matter, whether it's strange or not strange, because μs is also the chemical potential, the strangeness chemical potential is also 0. And so all particles should follow a universal pattern determined by their masses and spin degeneracies and by the hadronic mass spectrum. And you can see this very nicely. You see that even for the heavy systems, from omega minus on all the way to helium-4, essentially in this log plot, you see a straight line, which means that these are all given by Boltzmann factors. The slope of that line corresponds to this 156.6 MeV. You see, of course, that protons and lambdas and kaons and pions sit above that line, but that has to do with the fact that there is feeding from resonances into these states, and so they, of course, that has to be summed up, and you see that the bars, the horizontal bars include feeding, while the dashed blue line is the primordial thermal distribution, and you see that that describes the data very well, and that the full calculation, the total, approaches the primordial distribution as the masses become very heavy. Next slide. So the energy dependence of the hadron production is described not only at Lhc energy, but at all energies very nicely. And you see in these lines that these temperature and nu B values, how they behave as a function of energy. And you see that the temperature is special. It increases with energy below root S of 10 GeV, but then it levels off and stays constant, never mind what you do with energy. And in particular, the biggest jump in energy we ever did was between RHIC and Lhc, something like a factor of 20 in energy, in center of mass energy, and yet the temperature stays essentially constant, while the chemical potential decreases rapidly with higher temperature and approaches zero at Lhc energy. And all the details on the right-hand side, the particle yields and so on as a function of energy, are prescribed very well with an accuracy of better than 10%. Next slide. So here comes our description of the QCD phase diagram. Experimental points are added in this plot of T on the ordinate to baryochemical potential on the see that these points essentially provide our best information on the QCD phase diagram. The information from our theorists from either the hot QCD collaboration, which is shown here, and from the Wuppertal Budapest collaboration, which is in the reference there first, and also in Nature paper, agree very nicely with these experimental points up to baryochemical potential of a few hundred MeV. Above that in baryochemical potential, unfortunately, the lattice method, because for the insiders of the sign problem, is not anymore precise, and therefore this blue line, or this bluish greenish line, actually stops there. But this is really our best information on the QCD phase diagram and its comparison to the recent Lattice QCD predictions. Of course, if indeed the phase transition is a crossover for small mu, and if it would be a first order transition for very large mu, which is conjectured, then there must be a critical endpoint. And of course, you all know that there is a big search going on, in particular also at the RHIC beam energy scan program to look for that, up to now with no conclusive answer though. Okay, next slide. So let's make a brief aside on small systems, although I will go rather quickly here. So one can, next slide, one can actually analyze the particle production not only for central lead-lead collisions, but for more peripheral lead-lead collisions and for xenon-xenon collisions and for p-lead collisions, and finally for pp, and essentially map all available multiplicities and look at the multiplicity dependence of particle production. And this has been analyzed. This has been measured by the ALICE collaboration and analyzed in the paper you see right here. And if you go to the next slide, you see that the red points or the green points or the purple points and black points and so on, data for various hadron species. And what is plotted is particle yields against the multiplicity, and these are the points, again, are the data points, and the lines are the lines are predictions now of a similar model than the statistical hadronization model I showed you 3 slides ago, but before. But now, because the system becomes smaller and the number of particles becomes substantially smaller, one has to deal with what is called canonical correction, and that comes due to the fact that we need to conserve, of course, a strangeness number over the volume of the fireball, and not only in the slice at mid rapidity. And you see, if you do this, in particular, if you allow for this correlation volume to be larger than the fireball volume, as we have evidence from other measurements on the right-hand side, that even the complete multiplicity dependence of particle production can be understood quantitatively. And there are even newest results, which I do not have yet to show you, but they come also from the same people, from Christoph Redlich and John Clements and Natasha Sharma. And they show that even composite particles for the small rapidity densities can be included in that list. Next slide. So I will make a few comments on event-by-event fluctuations. So for that, one needs to know, in particular, the distributions of baryons and antibaryons if we want to measure the net baryon or net proton fluctuations. And there is a recent paper, which you can see here on the top, which is now actually just appeared in Nuclear Physics. And you can see the archive number, in which we describe how we obtain the rapidity distributions for net baryons from low energy to high energy. This is using actually the concept of limiting fragmentations, and all the details are given in that paper. I don't have time to discuss it here. But using that information for the rapidity distribution of protons and net baryons, so you see here on the right-hand side is net protons, and the left-hand side is net baryons, you can actually determine very well what the net baryon fluctuations should be. And this is explained in the paper, how to do that, in the paper on the top here. If you go to the next, I will go rather quickly. If you go to the next slide, you see that actually these are moments of or cumulants of net proton distributions described in canonical thermodynamics. Kappa 1 on the top left, of course, is first moments. And since I showed you that the first moments, which are the mean multiplicities, are described very well by that model, so that is by definition described very well. But kappa 2 and kappa 3 and kappa 4, you can already see some deviations. Now, interesting is, however, even though the canonical thermodynamics description is describing roughly the shape, but it certainly doesn't describe the details. But what is missing in here is, again, that we need to take account of conservation laws, and baryon number conservation needs to be taken into account. So in canonical thermodynamics, what I showed you before, and these are the lines which you see here, is that baryon number conservation can be directly taken into account. And that is leads to this description. If you go to the next slide, you see that, okay, what you saw is that this looks all very smooth, and we don't have any, there is no big or non-multiple effects in the data, at least not if we look at it the way we did. And you see also that if you want to use these net baryon distributions and determine chemical parameters from higher moments, you have to be very careful because these higher moments, again, are sensitive to correlations to the baryon number conservation. And actually, if you just do that, you get different results for chemical parameters depending on whether you take second moment, third moment, and so on, as shown here in this figure. So this is a much more complicated than the first moment analysis, which I showed you. So let's leave this UDS hadrons, just look at the yellow box here to remember, namely for baryochemical potential less than 300 MeV, which means essentially for all data from Brookhaven HES to CERN, CERN SPS to RHIC Energies and to Lhc Energies. We have a very good description of the experimental location of the QCD phase boundary, and the critical, pseudo-critical temperature is 156.5 plus minus 3 MeV if we use systematic uncertainties. Next slide. Now, let me take, how much time do I have? We'll have another 15 minutes or something like that.
Yeah, comfortably. Yeah.
Okay, so let's just keep on going and see how we can deal, whether we can deal in this context not only with up, down, and strange hadrons, but also with charm and eventually even beauty hadrons. So how about charm and statistical hadronization? Now, next slide. Let's go back and look at open and hidden charm and beauty in E plus A minus collisions. This is a paper from more than 10 years ago now, in which we analyzed the data from LEP at the C resonance. That means that the C boson, and you see the multiplicities of produced particles when this C resonance decays. And you see that here we have selected not the up and down. We have also analyzed that, but I want to focus on charm now. You see that you have D plus, D0, D plus S, and so on, all the way to higher Ds, to J psi, to psi prime, chi Cs, and then even B states. And the blue lines are our prediction for what should happen in this very small system, E plus A minus, and the red points are the data points. And when you look, you find very, maybe somewhat surprisingly, such a description works beautifully with a few obviously visible exceptions. Now, for you to understand what is actually done, I have to explain a little bit more. Because, of course, in E plus A minus, at the C boson resonance, essentially the dominant mechanism of particle production is via two jets. So you make E plus A minus goes to quark, anti-quark. The decays of the Z boson goes into quarks and anti-quarks, and they make jets. And these jets, of course, contain particles, and that is what is measured. Now, if you look, you see that the multiplicities of these particles are very nicely described with these blue lines. Of course, this is a log plot, and there are 8 orders of magnitude, and you see that there are clearly visible exceptions, which I will come to. Nice. That the quarks which are produced, the up, down, strange, charm, and beauty quarks are not produced in any kind of a thermal way. In fact, there are more B quarks than charm quarks in that calculation. And for each flavor, there is a separate normalization, and that normalization can be computed with precision in the electroweak theory. So the the flavors of the jets are computed as sort of input into this and not output. So that's very different from the heavy ion case. But once you know which of the quarks you actually have in there, you can ask yourself how it would hadronize, and that is what is described by this statistical hadronization. And you see that by and large this works very well with a few notable exceptions. You can see, for example, that if you look at shape psi, you have to be very careful, because it should not look at inclusive shape psi, which is the left part of the shape psi plot, but the shape psi primary, which is next to it. You see that there is something like 3 orders of magnitude difference between what we predicted and what the data are. And even worse, in epsilon production, this is even a much bigger discrepancy, and you cannot even describe these closed beauty or closed charm states, hidden charm states in such a scheme. And of course, that's simple to understand, because you would have to thermally produce a B quark to make epsilon, an anti-B jet, go into an epsilon particle. That is very strongly suppressed, and that is why this is not visible. So the fragmentation of these hadrons is quite well described, but only for open charm and open beauty states. Charmonia and epsilon states are off by many orders of magnitude. Next slide. Here, I will not go into that. You can later read it. This just tells you how this business with the electroweak theory goes in there. Next slide. So how do we include open and hidden charm into the statistical hadronization model? Well, let's look at the right-hand plot, and you see the same thing what you saw there before, the line, the up-down strange hadrons, and this blue dashed line and the solid lines above, which is our key result for up-down strange hadrons. And now if you plot into that plot shape psi, you will see that it is not at all following that line, but rather is sitting substantially above that line. That is quite surprising, but actually after a little thought, it turns out that it has a very clear physics reason why that is, and it's the key to how we actually introduce charm and beauty into the statistical hadronization. And the main point is that the shape psi is enhanced compared to the other mass 3 GeV hadrons, since the fireball at LHC has about 30 times more charm quarks than you would expect for pure thermal production. And that is because all of these charm quarks are produced in initial hard collisions and then subsequently thermalize. Enhancement factor, this additional number of charm quarks, there is about a factor 30 for these zero mesons. And that means if you enhance these charm quarks by a factor 30, you get the nice description of the D0 part. That is also plotted in these figures in the paper, which you see below the figure for the D mesons. And now you understand that shape psi should be much more enhanced because it has 2 charm quarks, and therefore the enhancement factor is 30 squared. And that actually fits perfectly with what the shape psi measured cross-section tells you in here. Next slide. So by this, the fact that this enhancement is precisely as predicted by the statistical hadronization model, that is, there is quadratic scaling in the number of charm quarks for Germania, that means these charm quarks can travel freely over the size of the fireball, which is of order of 10 Fermi. That is 10 times the radius of a proton. And therefore, the fact that this measurement is explained quantitatively in the statistical hadronization model tells us directly that the charm quarks are deconfined. So this is the first experimental proof for thermalized and deconfined charm quarks. And you can see more arguments outlined in the Nature, in the physics letters paper, and also in the Nature paper down here. Okay, next slide. So quantitatively, how one does that is one establishes what is called a charm balance equation that is in the middle of this slide here, where you equate the number of directly produced, that is in hard collisions, charm quark with that expected in a thermal approach, and you leave in there a free parameter G sub C. You can describe the total measured total number of charm quarks, basing it on this thermal number and leaving the possibility that you can enhance this thermal number by a factor G sub C, which I told you is about 30 for one charm quark, and therefore G squared for Germania would be 900. And of course, for particles with 3 charm quarks, we have not yet measured any, but they should be there. 27,000, a factor 27,000 enhancement. Well, actually not quite, and I will I will have to come to that, because for that you have to also use the same canonical corrections as we did for the strangeness at lower energy, at lower multiplicities. Next slide. So this is including the canonical corrections, and also I include in this slide more for your information, number of papers on the early development of this, all of this, where you can read in more detail. Next slide. So this factor G sub C is central to this. We call it a charm fugacity. I explained to you how one can determine it by equating the number of directly measured charm quarks. For that, you need to have the total charm cross-section in lead-lead collisions. We don't have that yet, but we have it in PP collisions, and so we actually extrapolate this to lead-lead collisions using the thickness function, the Glauber model. And if we do that, and we have to take shadowing into account, and if we do that, then we get that depending on the number of participants in the collision, this G sub C varies between something like 30 all the way down to 15 or so, or 50 when you come to a small number of end parts. Okay, next slide. With that, one can describe beautifully the psi distributions at Lhc Energies. I show you first only the data. You see that actually if you go from mid rapidity in green to from mid rapidity in red to forward rapidity in green, you see that the nuclear modification factor RAA actually drops the reason why that is, even though it tells you that it is not that the chip psi is suppressed, more suppressed at mid rapidity, but it looks like it is even enhanced, and this enhancement comes because of this factor GC and the fact that the ammonia are actually produced at the phase boundary, that is late in the collision and not early in the collision. And this thermal interpretation of germanium is also strongly supported by the fact that if you measure this nuclear modification factor as a function of PT, it is strongly peaked at low transverse momentum. And again, the biggest enhancement is seen for mid rapidity and less enhancement for forward rapidity. And you see all data from ALICE, CMS, and ATLAS in that plot. Next slide. And you see that actually quantitatively this describes both the data at RHIC and Lhc energy, and there is really no new parameter in there. It's the same, exactly the same parameters as we used for up, down, and strange hadrons, supplemented by the measured value of the open charm cross-section, which we now know quite well from measurements both at RHIC and Lhc energy. And you see that explains very nicely all the data both at RHIC and Lhc energy. And you also see that if you don't make that thermal interpretation, then you are at a loss, because the fireball, it certainly has a much higher energy density at Lhc energy compared to RHIC, but the blue data points are much smaller than the red data points. So it looks like, if you would talk in terms of suppression, that the ammonia are actually strongly suppressed at RHIC energy, but not suppressed, or nearly not suppressed, at Lhc energy. And that is exactly opposite to the model of germanium suppression, and of course it's naturally explained in the statistical hadronization approach. Next slide. One can go completely beyond that and actually predict the yields for charmed mesons, baryons, and exotic states. This is published recently, but there is also a new article in preparation. And again, you don't need any more new parameters to do that. And that is really one of the major advantages of such a description. And let's go to the next slide. So you see here a huge list of rapidity densities computed for any charmed particle you can imagine, even including omega CCC, which has 3 charm quarks. Of course, you have to take, this is still grand canonical, but you really have to take into account the canonical suppression, and that is done in the following slides. So next slide. Here we have yields for production of charm quarks, hadrons versus mass. Next slide. And you see here these yields are compared to the this is all for lead-lead collisions. So the canonical correction factors are not very large, even for NC equals to 3. So this looks like, you see all this charm hierarchy is visible, and it's the same hierarchy of mass and temperature as we have actually seen for the light particles, supplemented with this enhancement by the additional number of charm quarks in the fireball at Lhc energy. Next slide. So I'm at the end of my presentation. I have a few slides as summary. It will go very quickly. Statistical hadronization, I think, works quantitatively for hadrons with charm quarks. As I said, charm quarks are produced not thermally, but in initial hard collisions. And that leads to this charmonium enhancement, not suppression, but enhancement. And that, of course, we have now seen at Lhc Energies. That enhancement implies that charm quarks are really deconfined over large distances, much larger than the size of a proton. And we have seen that huge enhancements are predicted for multi-charm states, and hopefully with such enhancements, we can actually measure them in the upcoming periods, run 3 and run 4 and beyond. Next slide. So where do we go? Well, we can look into the hadronization of multi-charm quark states, and we can look at the correlation widths in rapidity. That, of course, means that we have to measure not only the mean values of charm states, but let's say we have to also measure net charm fluctuations. Like we measured net proton fluctuation, we have to measure net charm fluctuations. So charm minus anti-charm fluctuations, and determine from that the volume. We have to couple hydro to the system, and I showed you for the D mesons how well this actually works already. So we have that, and that can be treated. Beauty can be treated in a similar way. However, of course, we would need to get information on the thermalization of B quarks. Clearly, it would be interesting to extend the measurements to charm and beauty hadrons in jets. And as I said, this is something we look forward, and we should like to test the predictions from the statistical hadronization model and establish the deconfinement and this charm hierarchy with run 3 and run 4, and of course RD3 data. The next slide. So ALICE is currently being upgraded, so the TPC already runs with gem-based readouts. We have a new inner tracker with ultra-thin silicon layers, so that is ITS2, and hopefully soon in a few years ITS3. We have an expected increase of data rates in run 3 and run 4 by a factor of 50 over what we have currently. And so we can really measure rare objects, exotic quarkonia, double and hopefully even a glimpse of triple charm hadrons, and determine in detail the deconfinement radius for charm quarks, and settle the question of whether there are colorless bound states in a deconfined medium. And also settle the issue of how complex light nuclei and exotic charmonia are produced. We have speculated and published in our Nature paper that they may be produced as compact multi-quark bags, which then evolve into their hadronic configuration with a time scale which depends on the mass above the final real mass in the hadronic system. And of course, I said we would like to start measuring fluctuations, critical behavior, also near the phase boundary, not only for baryons, but also for charm particles.
I would like to thank Peter for such a nice discussion on this his model and the experimental outlook and how these things can be extended for the data coming in the future. So I would like to open this for discussion and questions. Peter would definitely like to answer some of them.
Yeah. Can I ask a question?
Please.
So, Peter, this is Vedang, and thank you for this nice talk. I have one question. There are lattice calculations as well as some QCD models, which suggest that C6 and C5 could, for net protons or net baryons or net charge, could become negative. So, and that would be a signature of.
Yes.
So, what is your views, and should we look at it at LHC, and because that's the ideal place? Yeah.
Well, I think indeed it's the ideal place because there we at least have a complete description of the phase boundary, and if one gets near the phase boundary, even if the transition is not first order, as it would or could be at a critical endpoint if it exists, but if one gets near the phase boundary, one should see, if you follow the Lattice QCD predictions you just mentioned, one should see critical behavior. Now, that of course assumes that one has all experimental issues for measuring such higher moments under control. I think we are ready in our lease to release the third moments measurements very soon. That is a question of months, maybe 2 months or so. And the fourth moment will follow very quickly. But up to the fourth moment, at least the Lattice QCD predictions are that things should be non-critical. And then our paper on the non-critical baseline will apply, and that would be an extremely important test. But the real issue is, can one go to the even higher moments? Now, that of course, the prediction for that depends on how large the fluctuations are, what that one expects. And if we make predictions using what we know best now, we should be able to get to that in the course of the next few years, provided the multiplicities for lead-lead collisions are as we have been told by the CERN accelerator specialists. But I should say, up to now, the CERN accelerator people were always very conservative, and in the end, they actually got more than what they predicted, and so we hope also that that will be the case. So I'm quite positive, and we certainly are gearing up towards measuring higher moments, including fifth and sixth. And since at Lhc energy barium chemical potential is 0, that of course includes also higher moments for charm particles. The odd moments actually should be 0 and will serve as a very good test how well one has corrections under control, and the even moments should contain the interesting information, and so we have to go to 6th order, and that will be extremely interesting.
Okay, yeah, thank you.
Tapanda.
Yeah, thank you, Peter, for this exciting talk on these statistical models. I'm really amazed by the way the statistical model is working, starting from the quarks to heavy quarks. And I have a question about the, I liked your description of the heavy quarks model. On the charm quarks, you said the charm quarks are produced early in the collision. then they thermalize. Happen. You have the recombination, regeneration, and all that. How do you account for that in statistical hadronization model, or can you apply the model?
Yes. So yes. So what we actually do, what we say, hadronization model is all hadrons and jumped particles like d mesons and lambda c baryons and so on. Of course, are hadrons. All hadrons are produced at the phase boundary. Now, so you have this fireball. It is filled with, as I said, a factor 30 more charm quarks because of these initial hard collisions than what you would normally have if there was only thermal production. So the system, if you like, we can treat the charmed quarks in the fireball like an impurity, using exactly the same mechanism in which people in solid states experiments introduce impurities into their system, and then you can still study phase transitions, including impurities. Because once the impurities take on, the same thermalization as the rest of the particles, you have a statistical system which includes these impurities. So this leads to this factor G sub C, as I explained. Now the system expands and eventually reaches the phase boundary, and in our case, presumably, the boundary is not really a line, but a transition, because the phase transition is not first order, but presumably a crossover phase transition. But nevertheless, over periods of, let's say, 20 MeV or so in temperature, all hadrons are formed. So all quarks disappear, the hadrons are formed. And the hadron formation now in the statistical hadronization model is done exactly the same way as it is done for up, down, and strange. Namely, we compute the thermal weights. And we also compute the thermal weights in a thermodynamical system at equilibrium that is completely well described by the statistical operator. And then, however, we do not need to deal with issues like in jets, as I showed you by E plus E minus, because now the system is one big fireball with all charm quarks along in equilibrium with up, down, and strange quarks. And then there is no more free parameters you need to describe. The only difference between the up, down, and strange parameters is this factor G sub C. And so G sub C enhances the D methods by a factor of 30, but it enhances charm hadrons with two charm quarks, like chi CC, but also charmonia, by a factor of 30 squared, which is 900. And that you have already seen, that works beautifully. Now, of course, we would like to see whether it works quantitatively for charm hadrons with two charm quarks, open charm hadrons with two charm quarks. And eventually, maybe we will succeed in even seeing something exotic like the omega CCC, but that's the trouble is this exponentially falling line, which I showed you. Maybe you could go back, if you still have the talk, you could go back a few slides to find this slide with the charm quark hierarchy. Can you do that?
I'm trying.
You're trying, okay. So while you're looking for that, there is nothing new in this description. A little forwards. More. Two or three slides more. Still more.
It's not moving.
Yeah, I don't know why it's not moving, but what I want to say is that there is nothing special about the hadronization of charm quarks. Yeah, go the other direction. Yeah, now further. No, more. No, the larger numbers.
Go forward or?
Yeah,
Go
go
forward
forward.
to larger numbers.
To 20.
Okay, go. Oh, here you go.
Go again.
Or you go to the end and you go backwards. Yeah, further.
The earlier one.
One more. Oops, one.
The table.
Up here. Yes. So you see that even with this Qc squared enhancement, if you look at the green lines, these are hadrons with two charm quarks, and you see actually the shape psi, that is this point at 3.1 GeV in mass, and that works perfectly. Unfortunately, we do not have a full cross-section yet for psi prime, and so all the rest are actually calculated points. This is the only point which is actually measured, the shape psi. And all the others should be also on that line, but you see that if you go from mass 3 to mass 4.5, you lose something like 3 orders of magnitude of yield. And already, you know that those of you, and I know there is a strong Indian community involved in measuring muons, ammonia via muons, and have struggled with trying to make good measurements for psi prime, which is only a factor of 5 or so, or 20 or so below the shape psi, maybe 50. If you go 3 orders of magnitude, it will be much, much, much tougher. And that is the real issue, but we will see. Maybe with an all-silicon detector, we can actually handle this also such that things will come out experimentally, but that is a dream up to now. Whether we can, but for establishing hadrons on that green line, we should get quite a few entries to test. And these are all predictions, of course, and as I said, there's no parameter. We cannot fiddle around with parameters in here.
Thank you so much.
Zubaida is next. Zubaida? Subhasita, you wanted to ask something?
Yeah, I have one
Go ahead.
question. Yeah, I have one question, Peter. Is that you talked about this is about higher moments and fluctuations in the charm sector.
Yeah.
Yeah, now, and if I understand correctly, the critical behavior you talked about at the critical endpoint. Now,
No, but no, yes, no. I think
yes, no?
critical behavior, I did not mean only the critical endpoint, because we would not be able to measure charmed hadrons at
That's
root
my
S.
question. That's exactly my concern, you can say.
No, impossible. So, as it turns out, if you analyze, like our friends from Lattice have done, the criticality, phase boundary, even if it's not a first order, the approach to that contains information on the critical behavior of the system. And if you actually do that, you should see, unfortunately, only in the highest moment, the sixth moment, you should see critical behavior. But I think realistically only for up and down quarks, that is net baryons. Maybe even net lambdas will be impossible.
Okay.
But this business of seeing the critical behavior near the phase boundary cannot be done in the charm sector. But the reason why we want to see fluctuations in the charm sector is that actually we have learned, and there is an Alice publication on that using these fluctuations in the baryon sector, we can actually learn about the correlation volume, the volume over which baryon number is conserved. And that volume turns out to be much larger than initially thought. And if the same would be the case also for charm, then in fact there would be significantly reduced canonical suppression, and that would be something which would help us, in particular if one wants to make use of slightly lighter systems like xenon plus or krypton plus krypton, where there is already significant canonical suppression. But that would actually help us to get more and more yields and more chance to actually measure area.
Okay. Okay.
Okay. Supriya, can you hear us?
Yes,
Yeah.
please go on.
Go ahead. Yeah. So can you please go to slide number 24? Yeah. So here you just wrote that the enhancement factor for GIPSA is 900 just because it scales with n cc bar square.
Yes.
But there are light quarks in the system like U and D. So shouldn't it be like n cc bar square divided by NU or ND?
No. Because to make a GIPSA, you have to live from the pools of C and C bar.
Right.
So now, NCC bar, or the CC bar, the number of CC bars squared comes about if the C's and the C bars are completely uncorrelated.
Right.
If you have a pool of particles that are completely uncorrelated, and you want to compute what the chance is that two of them hit, then you can compute, then that probability increases by the number of particles squared. Okay? If they're correlated, no, it would not do that.
Okay.
So,
And another
yes.
another question is regarding when you describe this PT spectra of charms with statistical hadronization model. Do you also consider some kind of expansion of the medium, the expansion dynamics?
Of course. I did not have time to describe what you actually see in here. On the left-hand side, you see that for D mesons, and the calculation is actually done by coupling the statistical hadronization model to the calculation of a hydrodynamic model from relativistic hydrodynamics. So the actual calculation, of course, treats that this is really the standard music, if you like. It is using this music hydrodynamics code for the flow of the charm particles, and that turns out to be, of course, extremely essential.
Okay. Thank you very much.
Rituparna wanted to ask a question. Rituparna, please go ahead.
Thank you, sir. So thank you, Peter, for such an informative talk. So I just like to know that when we are studying about the freeze-out parameters using statistical models, so can we apply the conservation of quantum numbers to all the ensembles while working with within a unit rapidity window for studying the particle yield?
Yeah. So very good question, of course, at Lhc energy, and if we deal only with up, down, and strange particles, it turns out that the conservation laws are not very important because we have so many, even strange quarks are in the order of hundreds, that all of this conservation business is not important for central collisions of Lattice. However, if you go to smaller systems, I showed you the multiplicity dependence computed by Redlich and Claymans and Sharma. If you do that, then you need to take that into account. However, you need to know, and that is important, you need to know that over what volume actually charm is really conserved. Now, if you go over the full fireball, measure lead collision, and you measure from rapidity -8 to rapidity +8. Of course, all quantum numbers would be conserved. For example, you would not measure any more fluctuations. The net baryon fluctuations are 0, because of course you don't violate baryon number conservation. The net charm correlation would be 0. So we already know that if we, as we have to, we can only measure over a finite rapidity window, that we have to take into account that there are correlations introduced by the question over what volume charm is actually conserved, or what volume baryon number is actually conserved. Now it turns out that much to our surprise, if we do this for baryon number conservation, we find that the actual volume over which baryon number conservation takes place at Lhc energy is much bigger than the volume of a fireball corresponding to 1 unit of rapidity. Now, in that calculations for lower multiplicities by Claymans and Redlich and Sharma, they have used first the same volume as the fireball volume of 1 unit of rapidity, and then they increased that volume, and they found that the results agree much better with a larger volume, which would be in agreement with what we have seen and published in others from the net baryon number. And this is a very active area of research, and I'm thinking, I believe there will be lots of interesting results coming out from that. But this is conventionally, up to now, most people have actually made that correlation volume smaller than the fireball volume for 1 unit of rapidity. It's a very good question.
Okay, so I just add one more question. So, what about decollision?
Is for light systems, there's also PP collisions. And if you can go back, unfortunately, the line numbers, I forgot to redo the line numbers. So not all slides have line numbers, but you have to go back about 10 slides or so. More, even more. No, you go the wrong way, you go forwards. Further. Yep, right here. Oops. Here. You look in these plots here, you see PP collisions are the open circles. The open circles are on the lower end, so something from, let's say, 2 or 3 of the n-charge data to something like, well, you see the open circles end up by something like 40 or so. So PP collisions are included in this. It uses exactly the same statistical hadronization approach we used, complemented by the strangeness conservation part, or canonical thermodynamics, if you like, but using a volume which is not equals to the fireball volume, but a bit larger. Okay, and you see that describes even for PP collisions, describes everything very well.
So
Okay.
one more question. So may I ask?
Oh,
Yes.
So what about this conservation of strange quark? What about the conservation of strangeness in this study?
oh, so that is this correlation volume here is the conservation of strange quarks, because we only deal here with, as you can see, K0 shorts, lambdas, omegas, cascades, and so on. And so the strangeness correlation was traditionally used to describe canonical thermodynamics for strange particles. What is actually done in this plot here is they even did the description of protons, which of course is not strange correlations. And we can discuss, that's a separate discussion how it goes, but if you focus on strange quarks, then that is precisely the correlation volume for strange quarks. And what the hints from this new result is that strange quarks may be correlated over a volume which is significantly larger than the volume of the fireball at 1 unit rapidity.
Okay, thank you very much for nice explanation.
So if there is no more question, we have come to the end of the discussion too. So at the end, I would like to thank Professor Peter Braun-Munzinger for a wonderful discussion on the phase space diagram, and a discussion following that to make the entire session very informative and illuminating for all of us. I'd like to thank all the participants for making it a success. Thank you, Peter. Thank you all. Thank you, Peter, for being with us, spending so much time from your busy schedule. I know that you are also, you are very busy till now. So thank you very much. Thank you for all.
Yeah, let me say just one sentence. I would like to thank you all for this opportunity, and in particular to thank the audience for interesting questions, which of course, as always, make me think and sometimes look at things in different ways. And I will certainly very carefully revisit this as I think about your questions in the future. Thank you very much.
Thank you.
All of you, and a very good weekend. Thank you and bye.
Bye.
Thank you.
Thank you.
Bye-bye.
Thank you.
How do I get out of this?